Evet. Okay guys, welcome back. So let's remember those models that we discussed. We discussed the FO. Sorry, let me change this color.
Hocam record almayı bu arada unutmadınız değil mi?
Efendim? Duyamadım sizi.
Kayıt almayı unutmadınız değil mi?
Çalıştırdım, evet.
Tamam.
Teşekkür ederim hatırlatma için. So we discussed the first order plus dead time. Okay, remember in this case g of s was given by our regular first order model with tau s plus 1 again, and also we had an exponential function with a time delay amounting to theta d and s. Okay, so it was an exponential function in the Laplace domain. There is also a second order with that time, although we will not spend too much time on this, but it's present. Okay, so you will hear about it. Second order plus that time. That is not surprisingly essentially a second order polynomial in the denominator, k e to the power minus theta ds. In the denominator you have a standardized second order expression, tau square s square plus 2 psi tau s plus 1. Okay, so this is the expression that you will find in the literature. But let's now focus on this term. Okay, the exponential term. Okay, e to the minus theta ds. Right, this is an infinite order polynomial. That's why systems which have time delay are also sometimes called infinite dimensional systems. Okay, so the reason being the exponential function, similar to any function, can actually be represented by an Taylor series expansion of infinite number of terms. Okay, as any function exponential function can be represented by an infinite series. So the most simple approximation uses a number of represented by an infinite series. Well, you know what that is, right? This is the Taylor series expansion. Okay, uses a number of terms from the Taylor series expansion. Okay, example, well, you can simply say that let e to the minus theta ds be represented by the first linear term of the Taylor series. So that's going to give us simply 1 minus theta d times s. Okay, so this is one simplest way of approximating the time delay. Okay, it's a polynomial of finite order, therefore it can be used as part of your linear system model as an approximation, and we will do this in our follow-up discussion, but this is not the best way of doing it. Okay, not the best available way, because for the exponential function there is a better approximation. And this approximation is not a polynomial, it's not a series, but it's a rational function. Okay? So Padé approximation, so-called, is a better way to approximate time delay with a finite order, finite dimensional rational function of S. Okay, let me give you the definition of the first order Padé approximation. There is also a second order, which we will not too much focus on. So first order Padé approximation simply approximates e to the minus theta d s as a rational function of s, which is 1 minus theta d over 2 s and 1 plus theta d over 2 s. Okay. Note, there is also a second order version which is even more accurate. But we will focus on the first order for our purposes. Okay? Now, what is that we note about this approximation is that it introduces to the transfer function 1 0 and 1 pole. So there will be an additional 0 and an additional pole as part of our transfer function. What is more, actually the 0 that is introduced is an unstable 0. Okay? So another note, this approximation introduces one unstable 0 and a stable pole to the transfer function. So that's not a property of the approximation itself. It is the property when it's used as part of our transfer function. Okay, within the context of system theory, feedback systems, if we use this approximation as part of the transfer function, we introduce an unstable 0 and a stable pole to the system representation. Okay, so what does it give us as a tool? Okay, this gives us a way to analyze the potential effects of time delay within a feedback system. Okay, so once we use this approximation, obviously what we can do is we can use it in order to analyze what's going to happen with our system. Okay, and that is our following example. Okay, so let's look at this on an example. Do you guys have any questions so far? So let me give you an example feedback system. Let's say that we have our regular single input, single output system with a P controller with a simple gain. So what's happening is that the system is given by a linear model of finite order. But what's happening is that in this system, the output is measured. So there is a sensor here. We will assume to be this sensor to be ideal. Gs of s will be equal to 1. But there will also be a transmitter, okay? Basically a communication link, transmitter. And that we will actually model as a pure time delay, okay? So here is our controller. Let me kind of draw the boundaries of the controller. This is my controller. Let me maybe just do some fixes here. Okay. So this is my K. Okay. So these are the boundaries of my controller. Okay. So communication delay is not part of the controller, but it's part of what's happening outside of the controller. So this is your wire out, and this point is your wire in that sense. Okay. Let's say the delay is described. Let me also verbally describe this. Okay. We have a remote sensor that communicates the output, communicates the output value to the controller with an 0.5 seconds communication delay. Analyze the effect of the time delay of this additional delay on the closed loop behavior of the system. Okay. Now let's take a look at what's happening without the time delay. Okay. Without the delay, what is the open loop transfer function? Well, we have G of S is simply, in this case, the two poles, S plus 1, S plus 2, right? So Q of, basically, the characteristic equation is equal to 1 plus K times G of S, right? So K times G of S. So that basically what I have is the root locus of this open loop transfer function, right? S plus 1, S plus 2. We have done this countless of times, right? Let me quickly sketch this for you. So we have a pole, open loop pole at -1, another open loop pole at -2. What is the number of asymptotes is 2, okay? And therefore the angle of the asymptotes are 90 degrees and -90 degrees. And the intersection with the real axis is just in the middle of these two poles. So that, and the real axis that is part of the root locus is this region over here. So what we have is a root locus that looks like this. So we have a perfect, throughout, not perfect, but throughoutly stable system. Okay? Any questions so far? So as k goes to infinity, these we go along these branches, and for k is equal to 0, we are at the open loop poles. Okay? Now what is interesting is what happens to this system in the presence of the time delay. Okay? So let's take a look at that. Now with the time delay, we have on the feedback path h of s is equal to 1 e to the power minus 0.5 s. Okay, so on the feedback path we no longer have a unit gain, but we have this communication delay. All right, so what is our open loop transfer function? It is given by k times g of s h of s, and that is equal to k e to the power minus 0.5 s over s plus 1 s plus 2. Okay, so with the Padé approximation, that exponential function simply becomes e to the minus 0.5 s becomes approximately 1 minus 0.25 s over 1 plus 0.25 s. Okay, so what is this equal to? If we kind of take out the 0.25 factor out, we will have minus 1 times s minus 4 s plus 4. Okay, so we have a 0 at s is equal to 4, and also we have a pole at s is equal to minus 4, and also we have a minus 1 constant. So that actually complicates the root locus process just a bit. Because of this minus sign, in fact, as k goes through the positive range, minus 1 times k goes through the negative range. So because of this minus 1, because of minus 1 factor, for k positive, we observe the negative gain root locus. Okay, we haven't gone through too much of the negative gain root locus, but it's the complementary locus basically. And I'm going to sketch it for you, and you can check this with MATLAB as well. Okay, so in this case, for example, instead of having an odd number of poles and zeros at the right hand side of the chosen point on the real axis, you need to have an even number of poles and zeros in order for that region to be included as part of the root locus. Let me make the sketch. So we have here our S-plane. Now what happens is that here is our minus 1 and minus 2 original poles of the system. There is an additional pole at minus 4, and there is another additional unstable 0 at plus 4. Okay? Now in this case, actually we still have two asymptotes because of the difference between the poles and zeros, but in this case the angles of the asymptotes are the complementary angles of the original root locus. Before we had 90 degree and minus 90 degree, now we will have 0 degree and minus or 180 degrees. Therefore, this region with even number of poles and zeros at the right hand side. So this region is not included, this region is included, and this region is also included. Again, we start from the open loop poles. Okay. And then basically what's going to happen is that you will have a breakaway point somewhere here. Okay, and then that's going to be the kind of root locus that we will have. Okay. So two effects that we have. One is that we introduce a stable pole and an unstable zero. And also we switch from the positive gain root locus to the negative gain root locus. Okay?
Hocam bu daha kötü yapmadı mı? Niye hani hem unstable yaptı sistemi hem de işte böyle yani
tamamen doğru, tamamen bir doğru tespit ama söyleyiş tarzınız sanki time delay'i biz isteyerek koymuşuz gibi düşünerek söylüyorsunuz.
olmak zorunda değil mi efendim?
Yani sonuçta communication delay yaşamak zorunda olduğunuz bir acı gerçekten ibaret. Yoksa sisteme isteyerek eklediğimiz bir şey değil. Doğru değil mi?
Doğru.
Yani tamamen doğru bir tespit arkadaşınızın söylediği. So it's a totally correct comment. But the way he said it is like we deliberately added the delay. It's not the case. The delay is an artifact of whatever is happening there. Communication delay is something that you have to deal with or you have to live with. So correctly identified is the effect on the system, which is basically a negative effect. We had a fully stable system with the poles being, closed loop poles being on the left hand side for all gain, positive gains. But now, with the presence of this half a second communication delay, we end up with the closed loop poles having a actually much smaller stable range. Okay, so note, okay, the stable range of positive controller gain K is much reduced. Okay, so this is a negative effect of the time delay on the stability of the involved system. Buyurun.
Hocam aslında bu yani K'yi limitleme sebebi zamanında K çok yüksek olduğunda zamanında stabilize etmek için geri çekilememesi mi? Hani anda tepki veremediği için. Time delay'in hani fiziksel olarak etkisi var mı?
Şimdi şöyle, sonuçta time delay'i tabii ki conceptually anlamak oldukça kolay. Şimdi siz diyelim ki kendinizi düşünün, bir çizgiye doğru koşuyorsunuz. Amacınız o çizgide durmak. Değil mi? Hani bulunduğunuz yerden o çizgiye gitmek bir step input gibi düşünün. Size çizgiye gitmeniz söyleniyor. Siz de bakıyorsunuz çizgi bayağı uzakta, koşmaya başlıyorsunuz. Çizgiye giderek yaklaşıyorsunuz. Ama ne yazık ki çizgiyi gözlemlemeniz yarım saniye gecikmeyle beyninize ulaşıyor. Öyle değil mi? O zaman ne olacaktır? Çizgiye çok yaklaştığınızda belli bir hızınız varsa eğer belli bir noktada çizgiyi geçme bilginiz size gecikmeli olarak geldiği için çizgiyi geçiyor olduğunuzu anladığınızda artık çok geç olmuş oluyor durmak için. Dinamiğiniz sizi öbür tarafa geçirecektir yani. Anlatabiliyor muyum? Yani gecikme sonuçta aslında bu tür psikolojik deneyler de yapılabiliyor. Mesela siz bazı sensörlerinizi, mesela görme sensörünüzü belli bir gecikmeye tabi tutarak size olan etkisini inceleyebiliyorsunuz. Mesela atıyorum bir gözlük taktınız, bilgisayar gözlüğü ve kameradan gelen görüntüyü size değişik zamanlarda geciktirerek veriyor. Bunun size olan etkisini doğrudan yaşayabilirsiniz yani. Ama kabaca düşündüğümüz zaman etkisini kestirebiliyoruz. Gecikme arttıkça bizim olan olaylara verdiğimiz tepki geciktiği için doğru tepkileri verememeye başlıyoruz artık. Biz geçmişteki bir olaya tepki veriyoruz. Şu anki durum ondan çok farklı olabilir.
Anladım hocam.
Başka soru var mı? So this is we can call this actually a kind of a result, right? So this is our result. And I have some additional notes or observations. One is that you have to notice that it really doesn't matter where the delay is, as long as the delay is on the open loop path. So the delay can be introduced from the controller to the plant. The delay can be introduced from the plant to the output, or the delay can be introduced from the output to the measurement, or from the measurement to the controller. Okay, as long as the delay is along that open loop path, the algebraic effect is the same, because it just comes in as a multiplier factor. And also you can have multiple physical effects for the delay, but because they will each introduce an exponential function, when you multiply all the exponential functions together, the exponents would be added together. So all the delays would be added together. Okay? So let me put that observation. The first one is that the results are independent of where the delay is introduced, is along the open loop path, and also all delays along the open loop path can be accumulated to analyze the effects. Okay, so if you have a physical system where there are different amounts of delays distributed along the control loop, all you need to do is basically account for every delay along the open loop path and collect them together in the form of a single delay. The mathematical effects will be the same. Okay? On what? On the closed loop stability of the system, the closed loop poles of the system. Okay? Obviously, different delays may have effects on different parts of the system with different effects. But if you mathematically consider the closed loop poles, the effects will be combined together. Okay? Now, let me give you an exercise. Use Raut-Horwitz criterion. Raut-Horwitz criterion to calculate the range of K for stability, A for the original system without delay, and for the system with delay. The good thing about the Raut-Horwitz criterion is that, as you know, differently from Root-Locus, it actually can analyze the entire range of K for stability, including negative K and positive K. So you just can come up with the full range of stable K very quickly and very efficiently. Okay, so I like Raut-Horwitz criterion to that effect, is that it's very easy to find that design range for K. Let me give you a sketch, and you can repeat this in MATLAB as well. Example. And for you to repeat in MATLAB or experiment with in MATLAB. Okay, a sketch of G of S is equal to a gain of 1 e to the power minus 3s over 10s plus 1. With ideal delay and with Padé approximation. Now, with the ideal delay, actually the sketch is simply the response of the system without delay, simply shifted by 3 seconds to the right, because ideal delay is simply a shift in the time axis. Okay, so if I wanted to sketch this, in fact, what I'm doing is I'm sketching a first order system with a time constant of 10. So, you know, in the ideal case, so this is our time and this is our y of t. The gain of the system is 1. So if this is our step input, what's going to happen is that the ideal system will have no response until 3 seconds. And then it's going to have a first order response like this. Okay, sorry, it's not very nice. So it's going to have a first order response like this. Okay, with obviously the slope crossing it at a particular time. Okay, and what about the how does the Padé approximation looks like? It will look like, and you can check this in MATLAB, as I said, it's going to have same thing until time 0, but then it will immediately generate a response. But this time, because of that unstable 0, by the way, unstable zeros have a name. Do you remember? They are known as non-minimum phase systems. Non-minimum phase system. Okay, if both the poles and zeros are the system are stable, the system is known as a minimum phase system. But if the zeros, there are zeros on the right hand side, it's a non-minimum phase system. Obviously, if there are poles on the right hand side, it's going to become unstable. So you don't talk about a minimum phase or a non-minimum phase. In this case, the response will be in the negative direction. But then it's going to come back and then it's going to match this system the rest of the way. Okay. So here is kind of the approximation effect. Approximation effect of Pade. Okay, and this is known as an undershoot. Undershoots do not exist for minimum phase systems, but if you have an unstable zero, you can see an undershoot in the system. Okay, this is characteristics of non-minimum phase systems. Okay, characteristic of non-minimum phase systems. From the real life, a typical example of a non-minimum phase system is a bicycle. Okay, for those of you who are kind of familiar with how bicycle steering works, in order to steer a bicycle, you need to first steer it in the opposing direction of where you want to turn. So if you want to turn left, you need to first steer the bike towards the right, and that's going to actually lean you into the left, and after that you will actually start to turn your steering wheel towards the left, and you will keep turning. So the initial motion of the steering wheel actually has an undershoot in it in order to turn, because the bicycle is a non-minimum phase system in terms of its turning dynamics. Okay? Okay guys, so do you have any questions so far? I have another example coming.
Ben şey soracaktım. Ideal delay dedik de ideal olmayan delay nasıl oluyor? Nasıl bir etki gösteriyor? Nedir bunu ideal yapan?
Ideal olmayan delay şöyle bir şey olabilir. Mesela first order bir sistemde, mesela first order bir sistemi sanki bir delay varmış gibi düşünebilirsiniz. Yani neden bir delay varmış gibi düşünebilirsiniz? Sisteme siz bir referans input uyguluyorsunuz. Ama sistem belli bir dinamikle o referans input'u takip ediyor. Yani siz buna şey diyebilirsiniz. Ya belli bir süre sonra referansı yakaladı. Yani burada bunu delay'miş gibi de kabul edebilirsiniz. Yani ben bir referans verdim. Sistemde belli bir gecikmeyle o referansı gerçekleştirdi. Ama gerçekte tam olarak bir delay'den bahsetmiyorsunuz. Aslında bir sistem dinamiğinden bahsediyorsunuz. Ama ideal delay dediğimizde tam olarak matematiksel olarak time ekseninin kaymasından bahsediyoruz.
Ya bütün zaman birimleri için geçerli ideal delay, değil mi?
Şimdi biliyorsunuz time invariant sistemler için aynen dediğiniz gibi, ama time varying sistemler için delay'in ne zaman gerçekleştiği sistemde ne olacağıyla ilgili bir hale geliyor. Tamam. Başka soru var mı? Okay. So I have another example. I'm going to start this example, but maybe I'm going to finish it offline. Let's start it. Okay. So this is another full example with the time delay. Example. If I can't finish this, I will share my notes with you with this one. So a plant with transfer function given by Gp of S is 0.8 over 1 plus 5S is to be controlled by a P controller. When you hear the P controller, you can know that you can apply everything you know from 302, okay? Because everything we learned in 302 are actually about a P controller, okay? Within the context of a PID controller, if it's a P controller, it is basically, you can apply anything that you want, root locus, Nyquist, you know, route Horowitz, whatever you want in order to design something for it. Okay. However, there is a communication delay of 2 seconds in the control loop. Find the stability boundaries or range of the system with and without the delay present. Okay. All right, so let's sketch our system. Okay, the unity feedback system actually has the following form. Okay, so as we said, so you can, this is our controller KC. Here is our system 0.8 over 1 plus 5s. So the time constant of the plant is 5 seconds. Okay. So here is our output, and we can basically put the delay in the return path. It doesn't matter actually where it is. Mathematically, the effect will be the same. Okay, so it's gonna affect the closed loop poles and zeros of the system, or the open loop poles and zeros of the system, and eventually it's gonna have an effect on the closed loop poles and zeros of the system. Okay. Actually, you know, the case of without a time delay is very, very simple. Without the time delay, let me do this with the root locus. Okay, so you have a single pole. Where is it? It is at minus 1 over 5. Okay, and what's going to happen is that you see the gain, overall open loop gain is, let's call this K. It's 0.8 kc. You have to just bear that in mind. Okay, kc and 0.8 are multiplied to become the open loop gain. So when you sketch the root locus, okay, and the root locus will look something like this, right? We have a single asymptote over here, okay, and what's going to happen is that here is 0.8 kc is equal to 0, and 0.8 kc simply goes to infinity. Okay, so what happens is that system stable for all kc positive. Okay, obviously if you use the route Horowitz, okay, for negative, right, for kc negative, you will have at this point somewhere you cross to the positive unstable part of the S-plane. Okay, so if you use route Horowitz or any other method to find out the j omega crossing, you can find for which negative kc you are actually crossing this boundary over here. You have to bear in mind that it's gonna you have to also take into account this 0.8 factor. Okay, obviously route Horowitz automatically does that. Okay. All right, so with the time delay, we will basically have a different open loop transfer function. So our characteristic equation will become 1 plus Kc times G of S, H of S. So that's going to be equal to 1 plus Kc times 0.8 e to the minus 2s from the time delay over 1 plus 5s. So with the Pade approximation, we have Q of S, this time approximately equal to 1 plus Kc times 0.8. Now I have 1 over 1 plus 5s as my original transfer function, but I also have 1 minus s and 1 plus s coming from the Pade approximation. Remember, it is 1 minus the half of the time delay times s and 1 plus half of the time delay times s. Okay, so let me calculate the characteristic equation equals 3. That's going to give me simply an equation, no longer to write that again. So I'm going to have 1 plus 5s times 1 plus s plus Kc 0.8 times 1 minus s equals to 0. The numerator of the characteristic equation expression. Okay, so if we regroup that, we will have 5s squared plus 6 minus 0.8 Kc times s, where terms are grouped together, plus 0.8 Kc plus 1 equals to 0. So this is your characteristic equation that needs to be solved. We will do that using the route Horowitz method. So let me construct the route array. Okay, so here we go. We have s squared term, s to the 1 term, s to the 0 term. The first two terms are from the polynomial. We have 5, then 6 minus 0.8 Kc, and then 0.8 Kc plus 1 and 0. Okay. Remember over here, because I have a 0 here, so I'll multiply these two divided by, so minus 0 divided by this. So I'm going to have over here the same 0.8 Kc plus 1. Okay. So for stability, no sign change in first column, because I already have a positive number here. Okay, that means all the rest needs to be positive. So I need to have 6 minus 0.8 Kc being positive, and that means 0.8 Kc has to be smaller than 6, and therefore Kc needs to be smaller than 7.5. So there is an upper limit on Kc, which needs to be 7.5. You can't go any further than 7.5 in the positive direction for Kc. And similarly, also I need to have the other term here also needs to be positive. So 0.8 Kc plus 1 needs to be positive, and therefore Kc needs to be larger than minus 1.25. So also there is a lower limit. If you go any smaller than minus 1.25, your system will become unstable again. Okay. In fact, there is also a negative limit for the case without the time delay as well, right? At this point over here, right? At some negative Kc, this system will also cross to the unstable side. Okay. But at least in the positive range, you have no limits for the positive Kc. But when you introduce the time delay, unfortunately, your gain is limited by 7.5. Now, why does that matter? In this example, for example, it matters for both steady state error, because this is a type 0 system, right? In order to diminish the steady state error, you actually need to increase the gain. You can do so indefinitely for the system without the time delay, but unfortunately, the system will become unstable after 7.5 if you have this communication delay. So you cannot make the steady state error too small because you are limited from the top for the amount of gain that you can apply to the system. Also, if you think about the settling time, well, settling time for a first order system can still be defined because the exponential function goes into a settling band in a similar way that the second order system is defined. So the settling time can be made much smaller here, indefinitely smaller. But unfortunately, if you have a communication delay, the system will become faster and faster. And then, unfortunately, when you cross 7.5 in the gain, system will become unstable. Okay? What's the time? 11:35. Okay? So this is finished, actually. Just exercise. Use Routh-Horowitz. Horowitz again. To find the lower limits on Kc for the system without time delay. I haven't shown you what that value was in the root locus, but you can use Routh-Horowitz criterion to just find that value. Okay? Any questions? All right, so if you want to leave, you can leave. If you have any questions, you can ask. Okay? Arkadaşlar isteyen çıkabilir. Sorusu olan, sormak isteyen varsa sorabilir.
İyi günler hocam.